I'll look at what I have in Google Classroom here for the week. Last week it was quiz week, so we had the quiz, we had lesson 3 and all that. Here's the video from class. If you wasn't in class or need to review what we did in class last week, that video is there. There was the Desmos video on how to graph a residual plot. The week before that, we had the Desmos on how to do the regression lines. So we've had a couple of Desmos videos. This week, I've condensed it down to just 3 things here. So we've had a lot in the last couple. I'm trying to keep it down. And I'll be adding our class video to this. But what we have in here is the handouts for class notes. There's 2 different ones that I'm using that I'll be doing here in class. So there's notes that you can print out and do with me, or you can just do it on paper. But I encourage you to take notes in this class. Here's the lessons. I've combined them into one document for lessons 4 and 5. So we're in unit 1, lesson 4 and 5. When you click on that, here's all this information. And in the lesson, it talks about exponential functions here. This blue is the answer. So if you can answer it without, what are the key features of an exponential function? Maybe you already know it before you read this. What's the graph of an exponential function look like? Okay. Student task. So this gives you a task right here. Most cars decrease in value over time, and it wants you to do this. And so here's where you fill that in your notes, and you try to do this. This is in the lesson. What's the initial value of the car? Can we model it with a function? Why or why not? How much does the value of the car decrease every year? And then you fill in this table demonstrating the value of the car over time. Then I've given you the answers right here. So you need to do it first and then check your answers. It says attempt the questions on this page before looking at the answers. The answers follow on the next page. It tells you right here that the answers are coming. So see if you can do that. All right, Ryan, glad to have you. So see if you can do that. And then after that one, I got another thing down here summarizing the task. That's part of this right here. When determining growth factors, there's more information down here on lesson 5. So you're supposed to use this table to answer the questions that follow. And again, there's 2 pages, and then the answers will be in the pages after that. So create a scatter plot of this data, and then try to answer these questions from it. Then here's the answers down here. I've got all the answers. Then the last thing we're studying this week is compound interest. So here's the lesson on compound interest. All right, so this tells you how to do that. And then you're supposed to complete the rest of the practice problems in the student handout packet for completing the assignment. So there's the lessons. So I've got the lessons, and then I got the assignments, the link to the assignment in formative. So when you click on that, it's going to take you over to formative to the lesson 4 and 5, unit 1, lesson 4 and 5 assignment. Loading very slow today, but it's there. Oh, there it comes. So yeah, the lesson 4 and 5 assignment right there. So got it. How many questions we got here? It's like seven questions. All right, so you've got all of that. The handouts we're going to go over here in class. Here's the lesson for you to read, which we're not going to go over in class, and then the assignment for the week, lessons 4 and 5, grouped into one assignment. So, all right, let's look at what I've got for notes today, what we're going to be talking about. And let's see, I'll get this and this. A few different things to write with here today. Lost my rep. Okay. Let's start with, this is 1.4 lesson. And we're talking about exponential functions still, right? So the parent function for exponential is f of x equals a times b to the x power, right? B to the x power. That makes it an exponential when the x is the exponent. That's how we know it's an exponential. So if b, the number that's being raised to the x, is greater than 1, then the function is exponential growth and is increasing. It'll be increasing. All right, kind of like this graph here, exponential growth, increasing. If b is less than 1, that number in there is a fraction because it's less than 1. This is exponential. I'm trying to write that clearly with this marker. Decay, right? And it is decreasing. So exponential decay would be decreasing. That's where the graph is starting up here and coming down as it goes farther into the x's. All right. So now let's take a look at the graph below. And on your notes, I've got this where it's right here. You can click on your notes. Actually, physically click on it, and it'll take you right here. And you'll have this graph in Desmos on your screen. It says, what do you notice as you investigate on Desmos? And what are some of the key characteristics you see? All right, so what do you notice about this? Somebody put in the chat or turn your microphone on. Tell me what you notice about this graph that we have right here on the screen. Exponential growth. Yes, we see growth as it goes left to right. As the x gets larger, the y is getting very much larger. And we see our equation is y equals b to the x. A is 1. I mean, a is not, there is no exponent. I'm sorry, not exponent. There is no coefficient because y equals a times b to the x. A is a coefficient. We don't have a coefficient, so a equals 1. We can put that there if it makes us feel better. 1 times b to the x. It doesn't change anything. And this says our b is 2. For this graph, b is 2. Now, we can change that. We can say x, the b is 5. Let's take it up to 5. So what's happened to our graph? It's gotten steeper. See, if we take it down to 2, watch the graph as I change it up. So it gets steeper and steeper. So the larger b is. Now, if I take b down to 1, it's just a straight line because it's 1 to the power of x. It doesn't matter what x is. 1 to the power of anything is going to be 1. So this is the equation y equals 1. So it's just a straight line. But when b gets smaller than 1, now as we get smaller, remember, if b is less than 1, this is exponential decay. And so we see that as the b, anytime the b is less than 1, we have an exponential decay graph. If it's larger than 1, we have an exponential growth. So Desmos allows us to do this where we can just hit this play button and it will automatically go from one end to the other. So steeper and steeper. Then as we go back down towards 0, becomes exponential decay anytime it's below 1. So the b will go back and forth there. So let me go back to our original one where b is 2. What's the domain in range? What's the domain of this equation? Who can tell me the domain of this function right here? Remember what the domain is. That's all the possible x's. All the possible x's. All real numbers, says Ryan. That's correct. Because this will go all the way to negative infinity for the x's. And even though it's getting bigger and bigger, it's still going to the right. It's still going to infinity. The x, you can have x of 1,000,000 on here, and it'll still have a value for y. It'll be a very, very big value, but it'll be a value. So yes, what about the range? The range of this equation. All right, so we're going to go ahead and, so since the domain is all the possible x's, the range is all the possible y's. And Ryan put 0 to infinity. Yes, and the 0, we put the parentheses instead of a bracket because the 0 is not included. This will never touch the 0. It'll just get infinitely closer and closer to the 0 as we go left. If I go there and just see that on the graph, it goes closer and closer. But even if we click on it over here, it's negative 15.31. It's not 0. It's just really, really close to it. We zoom in. And see, it's 0.00003. It's really, really close, but it never touches the 0. Never touches the 0 at all. So yes, it is from 0 to infinity, not including 0. Now let's look at this other link. Below that, there's another link on the same notes page. And now we have the same equation, but instead of A being 1, we can change A. So this is the exact same graph right now because A is 1. But if we make the A 2 or 3 or 5, see what changes now? A is 2. A is 3. A is 4. You see what's changing? A is 5. A is 6. What's changing as the A changes? A back down to 2. Now the y-intercept is where it crosses the y-axis is whatever value the A is. And when A is 5.6, it's crossing up here at 5.6. 5.6 is the y-intercept. So whatever the A is, if the A is negative, look, it goes negative down here because it makes it a negative equation. So now the negative flips the graph upside down. So all the negative values are down here. If A is 0, then we don't have nothing. Excuse me. Pardon me. If we have the A equals 0, we just have a line that a function equals 0. It's a line of y equals 0. But as A gets higher, it changes y. So if we just hit the little play button, it'll sit there and the A will go up to 10 and down to negative 10. We zoom out, we can see all of that. See what changes the y-intercept from 10 to negative 10. If we're doing the b at the same time, it gets all crazy because we're changing everything at the same time. Pause the b for a minute, let them go opposite each other. So it's just make dancing lines. Right? But no, Desmos just allows us to play with that with any value. Put it like we want to. All right, so let's go back. Let's go back to our notes here. So the domain and range, key characteristics, we know it gets increasingly bigger y as the x's increases. Or if it's decay, it gets increasingly small as the x increases. And the A, when we changed the A from a 1 to be other numbers, it didn't change the domain and range except for when A became negative. When A became negative, it flipped the graph upside down. Otherwise, you still had the same thing on there. Let's look at the back real quick of my first page of notes. Hopefully, you were able to observe some of these characteristics. The graph passed through the point 0, comma A. That's what we saw. The y-intercept was whatever the A was. The x-axis was an asymptote, right? That's where y equals 0. It never touched y equals 0, so that's an asymptote. The domain was all the real numbers, and the range is y is greater than 0 all the way to infinity if the A was larger than 0. But if A was a negative number, then it went to negative infinity. So we saw that. So, all right, so we have a problem here. Actually, we got a couple of them. We're going to do the first one. We're not going to do both of them because for time's sakes, we're not here forever. It wants us to graph this function. So we got y equals 1/2 times 3 to the x. All right, so what does the base tell me? The base would be the A, the 1/2. We're going to graph this. So where do we start? What do we do with that A? That is the y-intercept, right? We just talked about that a minute ago. So we're going to make that our right there is where it's going to cross the y-axis at 1/2. That's what that leading coefficient is. Now the base of 3 to the x, that's our base for the exponent. That tells us that we're multiplying by 3 every time the x goes up 1. I'm sorry, that's not correct. The x is going to be 3 to the x power. So like when x is 1, that's going to be 3. When x is 2, it's going to be 3 times 3. We are multiplying by 3 every time. When x is 3, it's 3 times 3 times 3. When 3 to the 4th, it'll be 3 times 3 times 3 times 3. So every time it's getting 3 times larger. So the base. So let's say 3 times larger. Leading coefficient is the y-intercept. Okay, so we got that point. Now it says find another point. So to graph something, we need to find more points, right? So if we say, okay, how about when x equals 2? So 1/2 times 3 squared, because we're going to make x equals 2. Well, 3 squared is 3 times 3, which is 9. So 1/2 times 9 is 4.5. So when x is 2, y is 4.5. So if we go to 2, 1, 2, 3, 4, right there's another point. We can fill in the point in between when x is 1. If that's a 1, that's just 3. 1/2 times 3 is 1.5. So we know at 1, it'll be at 1.5. So what is the asymptote for this equation? We got 1/2 times 3 to the x. Somebody put that in the chat there. What is the asymptote for this equation? We've got the coefficient, and we got the base of 3. These last two parts here is what I really want to hear from you guys. So one check about yourself is asymptote. Line close to horizontal line. Yes, an asymptote in this case is going to be y equals 0. Or you can say the x-axis, because that's the same thing. Same. The x-axis is the same thing as where y equals 0. So if we draw that, it's going to go all the way down here and getting bigger faster. Getting bigger faster right there. Going through our points. All right, so we graph that one. This is another problem. You can do this one. But we have a 1/4 as our base instead of the 3. So this one tells it every time it's 1/4 of what it was last time. So this is going to be exponential decay. Every time it's going to be 1/4 the size as it was before. And we're crossing at the 3 on the y-intercept. So not going to go through all of that, but it'll be good practice for you to go back and see if you can do that. All right, let's do the notes over here. All right, some of this is kind of a repeat of a little bit starting out, but exponential growth, this is using R and T now, because a lot of times in exponential growth situations, we talk about the A is the starting value, right? Starting value. Let's just start at the y-intercept. R is the rate of change, and T is time. Rate would be the same as the base when we saw on the other. So we would say our exponential growth would be A times R, put R in parentheses, T. I'm sorry. I have left one thing off. Let me change this off. Because we're talking about a difference between growth. This is a little different equation here. Growth and decay down below. If it's growing, when we write the equation, it should be 1 plus the R raised to the value of T. If it's decaying, f of x, A times 1 minus the R to T. And we will see some examples of that. And why am I putting the 1 in this equation? Well, let's look at that. Let's do a couple of examples. The original value of an investment is $1,800. All right, so that's our A. We know that's the A right away. So that's an important value. We need that one. If the value has increased by 7%, okay, 7% is our rate, right? That's the rate that's changing every year. Write an exponential function to model the situation. And then find the value of the investment after 15 years. All right, so first we have to write an exponential function that models this situation. So the key pieces of information we need is the A, and then is this going up or down? This says it has increased. So this is an exponential growth. So our function is going to say f of x equals A. We know what the A is. The starting value is 1,800. Increased by 7%. Now, we need this as a decimal because the rate should be a decimal. All right, so 7% is a decimal. Anyone know what 7% as a decimal is? If I want to make that a decimal amount, what is 7% if I write that as a decimal? I think most of you guys are asleep. 0.07. Very good. Thank you, Avery. So if we take 1 plus 0.07, that's 1.07. And to the t, or however much time we want to do it. So starting value, the rate that it's increasing and over the time. So if it wants for 15 years, we would say, okay, so f of 15, which means instead of x, we're using 15 as our time. Well, actually, I should say instead of t, because we use t, not x. F of t. So instead of t, f of 15 would be 1800 times 1.07 to the power of 15. And we need to know what that is so we can find the value of this investment. So let's pull up a calculator and put it up on the screen here.
There you go.
All right, so we've got a calculator on the screen, and we are going to do this equation right here. 1800 times parentheses 1.07 parentheses raised to the power of, we've got x to the power of y right here, raised to the power of 15. So 1800 times 1.07 raised to the power of 15 is 4966. And since we're talking about money, we would round that to the nearest two decimals because it'd be cents, right? 4966.26. Okay, so that investment, 4966.26, that investment has grown from $1,800 to almost $5,000, earning 7% per year for 15 years. It's more than doubled, and it's almost tripled. It's getting there. Let's do, there's another one. This is also exponential growth. Let's go down and do one of these exponential decays. It's the same A, R, and T. The same thing it is there. Still starting the value, the rate, and the time. Well, this rate is going to be a growth rate, and this is going to be a decay rate, right? And how much it decreases over time. So an investment of $12,000 is losing value at a rate of 4% every year. So write an exponential function to model this and then find the value of the investment after 9 years. Which, little advice, if you're losing 4% a year, you need to change investments. Don't leave it for 9 years because we're going to see how much money you're going to lose in a period of 9 years. So our function, f of t, starting value of 12,000, it's losing 4%, right? 4% is the same as 0.04. Right? It's how you convert that to a decimal. If it was 40%, by the way, 40% would just be a 0.4 or 0.40. Right? So make sure you know how to convert that. So with exponential decay, it's 1 minus the rate. It's only 0.96 because that's 1 minus 0.04 is 0.96. And basically what this formula is saying is that after each period of time, you've got 0.96 of what you had before. You got 96% left of what you started with because it's losing 4% each year. So you still got 96% left. This one we've got 1.07. We have 107% because it's growing 7%. So 96%. So if we need to find this after 9 years, we'll say f of 9 equals 12,000 times 0.96 to the 9th. Okay, back to our calculator. I'll move our calculator here since I put our formula over there now. So 12,000 times 0.96 parentheses raised to the power of 9. We've only got $8,310 and 41 cents. We've lost a lot of the money. Started out with $12,000 and now we're down to $8,300 just because it's losing value. You need to move that investment. Here's another one for you to practice with. Same thing. This one loses 8%, starts at 35,000. Find the value of the car at 2015. Now, I will tell you, anytime you have one of these that deals with years, all right, like this one deals with the years, it's best to make this year zero. This is when you started. 2008 would be year zero. Year zero. And so this would be looking at 7, right? Because it'd be 7 years later. So find the value of the car in 7 years. Right. So you start with this rate, it goes up, goes down 8% a year, and you find it for 7 years. So, all right, let's turn this over. Got some more examples, more practice problems. So we'll go ahead and do one of these, and then we'll look at the one on the back with a table. So let's pick one here. Let's use this one. This has a year in there, so let's do that. The average price of a movie ticket in 1990 was $4.22. So our function starts with function of time starts with 4.22. The price has increased. That tells us whether or not we're adding or not. Add 1 plus 3.1%. All right, now don't let that extra decimal confuse you. Think about 3% is still 0.03, except you've got another decimal after it. So it's 1.031. Still, to make the 3.1%, you just move the decimal over 2 spots, which means you got to put a 0 in front of it. 0.031. You're just moving the decimal over 2 spots to convert this to a decimal. 0.031. And that is to T. So to figure out 2016, what's the price of a ticket? F of how many years has that been since 1990? Well, if we subtract 1990 from 2016, that's 26 years. So movie tickets was $4 in 1990. So we'll start out with our $4.22. It's increased 3% per year for 26 years. So let's see what the average price was in the year 2016. Okay, so we'll start with the 4.22. You need to practice enough of these to where this gets easy. 0.031 raised to the power of 26 years. So over 26 years, price jumped up to $9.33. And I think the price is growing faster now. Tickets are running, what, $12 or something now? They're getting pretty high. 12, $14. So that's how you do that. Is write your exponential. If determine whether it's a growth or decay, so you know whether you're adding it to 1 or subtracting it from 1. And then figure out what your time is. 1990 to 2016, 26 years. Okay, same things here. Virus has infected 400 people and spreading to 25% more people. See, the key is more people. So that tells you that's an increasing, that's a growth. All right. This is a cancel increase, that's a growth. So look for those key words. Population in a small town, and the population has decreased. That's decay. Your car depreciates. That's decay. So look for those key words that let you know, am I writing an exponential growth or an exponential decay? All right, let's go over to this table now because this changes up just a little bit. All right, the table to the left shows the year and population in millions of Texas. How many millions of people there are in Texas from 1900 to 1980. Using an exponential model, Okay, exponential model. That goes back to what we've been doing with the regression lines. Exponential model. Write an equation for the curve of best fit. Curve of best fit. That's the regression lines. That's what we were doing in our earlier lessons. Then we're supposed to estimate the population in 2020. All right, so this is one of those cases where if this is our starting year, for our purposes of the table that we're going to use, we're going to call that year 0. All right, that's year 0. And then we can do this as however you want to do it. If you want to say that we're going up 20 every time and that's 1, or we can just go 20, 40, 60, 80 up to 120. So let's try that. Let's see if that looks reasonable. So this would be 0, 20, 40, 60, 80. Starting with 1900 as year 0. So we're going to go to Desmos. All right, so here's a Desmos graph we got right here. I'm going to cancel this graph we had on there. And let's put this table. Starting at year 0, 20, 40, 60, and we have 80. And it's in 3.1 million, 4.6, 6.4, 9.5, 14.2. And we didn't have any data for the year 2000. All right, so that is our graph. Here, we zoom out a little bit. We start to see there. And it told us to use an exponential model. Exponential model. So we've got to use the y1 and the x1 so we can use this table's data. Exponential model is y1. Remember, we'd normally say equals a times b to the power of x, but, x1. But if we want it to do the line of best fit, we got to use that tilde, which is up in the corner of your keyboard, the tilde. And there, see, it made the line of best fit, and it goes right through those lines. That looks like a very good line. Right? That's a very good line. Right there. So that tells us what our growth rate is each year. And it's 1.019. So if we want to say we'll round to 2 decimals, so we'll just call that 1.02. 1.02. So our B will equal 1.02. All right. So let's go back to look at this now. We found our B. So let's write our equation. F of x equals, we know the starting amount at 3.1. I know it had a little different starting amount for that line of best of fit. It has 3.03. So it's a little bit smaller than what our actual line is. See, it's a little off if we zoom in, because we know that's the actual starting point. So we'll go ahead and use the 3.1 since we know for sure that that is the starting point to use. So 3.1 and 1.02 was the growth to the power of x. So we want to know in the year 2020. So we're going to say, okay, if 1900 was year 0, f of 120 years later equals 3.1 times 1.02, 120 years later. Let's see what the population of Texas would be. All right, so we'll pull up our our calculator. Let's clear all that out. 3.1 times parentheses 1.02 parentheses to the power of 120. 33.37. They did it to 1 decimal. They did it all to 1 decimal here. So since they did 1 decimal, we'll take it to 1 decimal also. So now it says 33.4 then. So this estimates, based on this population growth, that there's 33 million people in Texas in the year 2020. We can look that up now. It's past 2020 to see if that's accurate. But based on this historical data, that's what it predicted that the population of Texas would be. All right. Now you could do this with using 1900, but your number is going to really change in Desmos. Let's just do that, see what it shows us. If I made this 1900, 1920, 1940, 1960, and 1980, it changes our A. It's got an A that's got 15, it's a decimal, 0.0 with 15 zeros and a 3. But we still will get the same B. So if we're just needing to get the B out of it, we'll still get the right growth rate, 1.02 on the growth rate. It's just that your y-intercept is going to be a crazy number. So that's why I changed that to 0 on that if you're needing all of that. So, all right. Let's move it on. This is another one, so you can try that one. It does the same thing, exponential model, curve of best fit. So you go back to Desmos, do the same thing, except enter in this information instead of this information, and see if you can do it. All right, so that's another practice problem for you. If you can't do that, get with me. You need to be able to do this. All right, we're going to skip these notes. This just talks about some of the key features of exponential functions. We did that back in lesson 1. All right, lesson 1. So, what's a graph look like of exponential functions? All right. How are linear and exponential functions similar and different? That's all from lesson 1. This is in those notes. This is the part of it where I said the answers are on the next page. So you're supposed to do all the values of this car and then fill in this table. And then the answers are in your lesson. So this is all in your lesson, this table here. So you're supposed to practice that, see if you can do that alone. So let me turn back to the next page that we're going to go over here in our class today. Okay, I want to look at this because this is a little different. Writing an exponential function from 2 data points. We don't know the growth rate or the decay rate. All we know is 2 points in time. 2 points in time. So we want to look at these 2 points in time and see if we can pull some information out of that we can write our own equation with. So let me see my notes on this. I made some notes on this earlier so we wouldn't mess it up here. All right. So if we have 2 points, so you're going to pay attention to this one because it's a little different. Dylan releases new music on one of his social media platforms. One particular song of his had 500 listens on the day he released it. So that's day 0. That's the day he released it. And 1,725 listens 5 days after he released it. Write an exponential function model, exponential, for the scenario, and use it to estimate the number of listens he might expect to get at day 21. Okay, we don't know the growth rate. All we know is 5 days later, it had this many. It started out with 500, and 5 days later, it had 1,725. So we've got to figure out, based on, I'm gonna put y equals a times b to the x. I write it in y equals. That's the same as f of x. I just didn't write it in function notation. All we know is at day 0, which we have that point, 0, 500. And we know we have another point at day 5, 1,725. We know the x, when x is 0, the y is 500. When x is 5, I need to make that 5 a little clearer. When x is 5, the y is 1,725. Well, here's how we can do that. Let's substitute what we know into these equations. So the y is 500 equals a times b to the x is 0. Okay, that is one of the equations we have. And if we simplify that, b to the 0, anything to the power of 0 is 1. So this is 500 equals a times 1. So this just tells us that our a is 500. Okay. A is 500. We knew that. That's day 0. We know what the starting amount was. But this just mathematically, that's the same thing putting it into our equation. But let's look at day 5. The y on day 5 is 1725 equals a times b to the x is 5th. All right. Well, we know that the a is 500, so we can substitute that in here. 1725 equals 500 times some rate to the 5th power, b to the 5th power, whatever rate that is to the 5th power. So we need to solve this for b. We need to figure out what it is. So since it's 500 times b to the 5th, let's divide both sides by 500. All right, 1725 divided by 500. So over here, we know this equals b to the 5th. Because 500 divided by 500 is 1. That just leaves b to the 5th power. Let's see what 1725 is when you divide it by 500. Clear. 1725 divided by 500 is 3.45. So we're almost there. We don't know what b is, but we know what b to the 5th power is. So how do we get b if we have b to the 5th power? Well, let me think of it differently. What if you had b squared? If we had b squared equals 4, how can we figure out what b was? If we had b squared equals 4. Put that in the chat. If we had b squared equals 4, how would we find out what b was? Square root of 4. Yeah, we take the square root of both sides. We'd say, okay, the square root of that, the square root of that. Square root of b squared is just b. Square root of 4. If we're talking about a distance or value, we know it's positive 2 because there's also could be negative 2. But in a scenario like this, we would know it'd be a positive number. So b equals 2. Well, that's what we do when we have the square. When we have the square, b squared, we take the square root. If we have b to the 5th, we take the 5th root. All right, so what is the 5th root of both sides? Well, the 5th root of b to the 5th is just b. What is the 5th root of 3.45? There's a couple of ways to do that. Let me show you with the calculator that's built into the computers here. If I got 3.45, I can, instead of to the power of y, I can do the shift, the second, and now it's saying to the root of 5. So I say to the 5th root. And it's 1.28. Now I know how most folks are going to do this because this is quick and easy. You're going to open up a Google page and you'll just say, what is the 5th root of 3.45? What's the 5th root of 3.45? It's 1.28. You can pull it right up in Google and just ask it what the 5th root is. You just type 5th root instead of square root or 3rd root. So 1.28 is the number we're looking for. So the b equals 1.28. So our equation then for Dylan's music is y or f of x, wherever you want. The a was 500. The rate is 1.28 to the x or to the t. If you want to use t, you can use t. But we're going to do the x. So it wants to know 21 days later. So if we change that x to a 21 and do the math, okay, 500 times 1.28 raised to the power of 21, 89,202. We're going to round that down automatically because we don't have a partial listen, like somebody listened 0.98 listen. We'll just cut that off because in a real world situation, they haven't listened to that 203rd time yet. They're almost there at 0.98. But that's how we can do that when we have 2 points. Now let's see, just for our sake, what would Desmos do if we only have 2 points in our table and we tell it we want it exponential? Let's see how close it gets to the 1.28, because Desmos is pretty sharp. So if we only have 2 points in our table, and one of them is 0, and the other one's when x equals 5, and this is 500, and this is 1725, and we tell Desmos we want that exponential a times b to the power of x1, 1.28. It came up with the same thing. Excuse me. Pardon me. So even Desmos, doing that line of best fit with just 2 points, came up with a pretty accurate value. Now it's way up here. We got to zoom out a long ways to see it, because the y-intercept's at 500, so it's going to be way up there before we cross the y. There's the y-intercept. But even Desmos, with the line of best fit with just 2 points, if we tell it we need it to be exponential, still came up with the 1.28 that we came up with. So you can do that with Desmos if you make sure you're using exponential or whatever type of formula you're supposed to be doing. And this tells us to use exponential. 1.28. 500 times 1.28. All right, very good. See what other notes we need to cover today. We do have, there's more practice problems. All right, more practice problems. All right, we're going to do compound interest. And I think that's the last thing we're covering today. Compound interest. This is just good to know for life right here. We're talking about compound interest. How much money are you making on money that you put in the bank or in an investment or something along that lines? So there is a formula. Here, I'm going to use the pen so it looks a little clearer on here. The amount is, and I'm going to write this formula and then we'll go through it. 1 plus R divided by N times T. Okay, that is the formula for compound interest. A equals P, parentheses 1 plus R divided by N, raised to the power of N times T. All right, N times T. So let's talk about what each of these are. The A is the amount. That's the amount of money you got, right? Okay, that's just the amount. P is your principal. That's your starting amount. All right, that's starting. How much money did you invest to start with? How much did you put in the bank account? How much did you put in a CD? How much, whatever you invested in? That's the principal. R is your interest rate. It's your rate. And again, that's a decimal. Your interest rate is a decimal. N is the number of times that your interest is compounded. So I'm going to say compounded. Number of times compounded per T, and T is time. So the number of times compounded per T, and T is time. So let's do an example or two so we understand how to use this formula, because it looks like a lot of pieces. It's not too bad. Okay, Laura deposited $12,000. Okay, so that's the amount we need because that is the starting principal. All right, that's their starting principal. That's how much she deposited into an account that earns 8% interest. Okay, so that is our interest rate. We just need to convert it to a decimal. How much money will she have in 5 years? There's our time. If the interest is compounded quarterly, so our N is quarterly. So if something's compounded quarterly, how many times per year is it compounded? Somebody tell me that. If you compound something quarterly, how many times per year? All right, I see a 4 in the chat. Ryan's on top of it today. She's answered most of you guys' questions. Quarterly. If you have 4 quarters, you have a complete, right? 4 quarters in $1. You have a complete dollar. If you have 4 quarters, quarterly means 1/4. So that means 4 times a year you get interest. So 8% interest you'll get every quarter. You'll get 1/4 of it each quarter. Now, the thing about compound interest is every time the interest is figured, it's figured on how much you had before, including the interest you were given before. So you're getting interest on top of the interest. Every quarter, you're getting interest on top of the interest. So that's why compound interest is a wonderful thing. So let's do this equation. Now let's do this one in black here. So the amount would be, our principal was $12,000. 1 plus our R is 8%, but we need it in a decimal. So it's 0.08 divided by our N. Our N is 4 because it's quarterly. And all of that raised to the power of N times T. 5 years times, so it's 20, because 5 times 4 equals 20. Because our N is 4 and our T is 5. So to the 20. So let's see how much money we have. So let's pull up our calculator. Again, we'll say we're starting $12,000 and we're taking that times 1 plus 0.08 divided by 4. All right, raised to the power of 20. So that will grow in 5 years to be $17,831.37. That's pretty good. 8% interest, $12,000 can turn into $17,000 in 5 years if the interest is compounded quarterly. All right, quarterly. If your interest is only compounded once a year, it'll be substantially less. If it's compounded monthly, 12 times a year, it'll be more because you're getting interest on top of interest each time, and your interest is growing faster. So let's look at the second one. Oh, no, let's look at the last one because that's everything. Let's suppose you invest $750 into an account that pays 3% interest, so only 3%, but it's compounded weekly. I haven't seen a problem with weekly before, so we're going to do this weekly, $750, 3% interest, and we want to know after 20 years. All right, so we're only starting with $750. Let's write our equation for this one. So our amount will be our principal, $750 times the 1 plus. So what's our rate? 0.03, 0.03. But we get a fraction of that every week, 52, right? Weekly, there's 52 weeks in the year. So we'll get 1/52nd of that 3% every week. And up here it's going to be N is 52 times 20. 52 times 20. So we're going to get it like over 1,000 times. I put the 20 in parentheses there. So let's put this in our calculator and see how much our $750 turns into. You have to set this up right, or you won't have any chance getting the right problem. But 750 to get the right answer times, okay, parentheses, 1 plus. Now we can just type the 1 plus 0.03 divided by 52 because the order of operations will tell it to do this first. Order of operations, the calculator will automatically do that first because dividing comes before adding. Then raised to the power of, and then we'll put it in parentheses, 52 times 20. So it knows all of that is my exponent. So we look it up here at the top of this calculator. It's got 750 times 1 plus 0.03 divided by 52 raised to the power of 52 times 20, which is 1,040. And our $750 turns into 1,366. It's almost doubled at 3% interest. 1,366 and 35 cents. $0.35. So at only 3% interest, it's almost doubled because you're getting interest paid to you every week. Every week. So as you can see, there's extra problems here for you to practice. So if you don't think you understood this very well, go back and see if you can do some of these. These are in the notes in Google Classroom. This is the class handout notes. So look at these and see if you can work these problems. Just take a piece of paper and see if you can work these problems. And if you think you've got the wrong answer, get with me. Here's more over here, more practice problems. There's several of them here on the back on the next page too. And then there is some with a table. There's plenty of practice problems in all of these. All right, so that's back to the beginning of our packet. So, all right, I've taken an hour of your time for this. There's a lot to go over. I know that we have a lot in this algebra class that we have to go over each week, but I'm really working hard not to have multiple classes per week. Because a lot of time these pre-AP college board classes, they have to meet 2 or 3 times a week, and I'm trying to avoid that with virtual school to allow you guys some time to read, practice some things on your own, because normally we would do all those practice problems in class, and I would keep you here and you would do them here. I'm trusting you to do this on your own because this is virtual school. You've got some of that flexibility and some of that freedom to do that. So get your piece of paper, take some notes. If you need to go back and watch this video, I'll have it posted in Google Classroom a little later, and that way you understand what's going on, because we're going to get to the end of this and start doing some quizzing and testing a little bit later. So, all right. If you got questions, hang around. I'll work with you. Otherwise, have a great week.